Today, we're going to learn about another type of sequence, a geometric sequence. So for the arithmetic sequence, right, we said each successive term, right, is sort of generated by adding the same number. Well, here, we don't look at the difference. So for arithmetic sequences, we looked at the difference between successive terms. Here, we're going to look at the ratio between successive terms. And if it's a geometric sequence, then the ratio between successive terms is a constant called not the common difference, but the common ratio, R. So for example, take a look here. Determine the common ratio and find the next three terms. So you take these two, and you're going to do R is equal to A2 over A1. So 9 over negative 6, negative 1.5. You can do, okay, so depending on how the sequence is given to you, you can either put it in terms of decimals or fractions, right? But it looks like this is going by decimals. So now the next few terms then are, so you take negative 13.5 multiply by negative 1.5, 20.25. Then you take 20.25 multiply by negative 1.5, and you get negative 30.375. And then the next one, I believe, is 45.563. Okay, so those are the next three terms. All right, questions? Okay, this next one is given in terms of expressions. So you take this over that, and R is negative 81n plus 243 over 243n minus 729. And guess what? You can actually factor out a negative 81 from the top, and you get n minus 3. You can factor out a 243 from the bottom, and you get n minus 3. Oh my gosh. So R is negative 1/3. Isn't that funny? Okay. So the next few terms then, all right. So if this is A1, A2, A3, A4 is negative 1/3 times 27n minus 81. Negative 9n plus 27. Then you multiply that by negative 1/3. Right? So you get 3n minus 3. No, minus 9. A6 is negative 1 over 3 times 3n minus 9. Negative n plus 3. Okay? All right. Questions? Okay. So let's come up with a formula, right? Let's come up with this formula here. So suppose we have a list, or a sequence rather, right? We're going to come up with a sequence. I want to make R equal to 2. Okay? Now suppose A1 is 3. Okay? What's A2 going to be? Right, because it's going to be 3 times 2, correct? A3 is going to be 3 times 2 times 2, right? Which is, okay, so A4, 3 times 2 times 2 times 2. So what's the pattern? So if you look at A2, that's 3 times 2 to the 1. Then A3 is 3 times 2 to the 2. 3 times 2 to the 3. What would be A1 in that pattern? 3 times 2 to the 0. Right? So do you see a connection? So if you go further down to AN, then AN is going to, so there's always that A1 term, right? A1 times, what was the 2? R to the power of how many? N minus 1. Okay? So that is the explicit formula. Okay? Now, the recursive formula is A1 equals whatever value, and then AN is R times the previous term. Okay? All right. Okay, so I actually want to talk to you guys about a little pattern here. So look, for the arithmetic sequence, remember how we said AN is equal to A1 plus N minus 1 times D? And then remember how we said that's like, you know, that's sort of like y equals mx plus b, right? Well, the geometric one is AN is equal to A1 r to the n minus 1. So, you know, A1 is not changing, right? A1 is like the same term every single time. So that's a constant. Let's just call it A. R is another constant. Let's call it B. What would change, like, if you keep progressing? So this exponent always changes, right? R to the 1, R to the 2, R to the 3. And then this AN always changes, right? When R is 1, A is 3. When R is 2, A is 6. R is 3, A is 12. So this is changing. We'll call this Y, and we'll call this X. So do you see how the formula for the geometric sequence is an exponential formula? It's an exponential equation, whereas for the arithmetic, it's a linear. Okay? So if we were to plot successive terms of a geometric sequence, it would look like an exponential graph. Isn't that cool? Super cool. All right. So write an explicit formula and a recursive formula. So this is the same exact thing as in section 1, but now we're going to apply the new formulas to them. So what do we have here? A1 is negative 1. R is 2 over minus 1, negative 2. So explicit AN is A1 R to the n minus 1. This is negative 1 times negative 2 to the power of n minus 1. Okay. All right, next one. And then, so the negative 1 here, you can like leave it out. And then you'll know that A1 will be, you know, if n is 1, this will be 0, so it'll be negative 1. Okay? Okay, so the recursive, you say, okay, A1 is equal to negative 1, semicolon. AN is equal to whatever R we got, negative 2, times A n minus 1. All right? And the parentheses are not required, so you could also do it like this, negative 2A n minus 1. Either one of those is okay. Okay. Any questions? Yeah.
Just to like triple check, the recursive formula is again double.
Yeah, when you have to, in order to get the next term, you have to look at the previous term. Okay, find the 11th term of the geometric sequence.